This first one is a classic physics question. Classic in that it's been on a lot of physics exams. This begins with the idea that this is a ice hemisphere. This is often how this is explained, that this is a ice hemisphere. And they'll give some dynamic pieces of information, like, it has a radius of r. Oops, that's not so much what I wanted to do. I do not know what's going on today at lunch, but there's some craziness and shenanigans going on at lunch today. The idea behind this problem is that if a child were to sit at the very top, then they would slide down, of course, along the side. However, if you think it all the way through, as they slide, they would accelerate because there's going to be a component of their weight that's going to be downwards. Well, in order for them to stay on the sphere, there has to be a normal force that acts on them. But for them to travel in a circle, there has to be a radial acceleration that is great enough to keep them curving in a circular path. It is possible for them to go fast enough to leave the sphere and become airborne. I'd like you to figure out at what angle that happens. This is a classic question and one that I think is a good place to start. It will demonstrate a lot of the stuff we've talked about. This problem has a couple of neat components in it that I really do like, but like I said, as a classic question goes, it actually has been on the AP exam, even though it's in almost every single textbook that's out there for physics. So what I would like you guys to do, since you guys are pretty sharp, and I'm at least as sharp as third period, is I would like you to come up with an expression for the guys' kinetic energy as they slide along the sphere. Meaning I would like the kinetic energy as a function of theta. I'll allow you to use m for the mass of the person. I'll allow you to use r for the radius of the sphere. I'll allow you to have theta in there and any fundamental constant you want. But what I'd like you to be able to tell me is, what is this guy's kinetic energy? Because basically that's also telling me what his velocity is at any point along the sphere. Let's go with 120 seconds on that. So let's all make at least one grand assumption. The guy has energy equivalent to mgr when he's at the top. So when they're here, how high are they? Right, that's more like a rhetorical. So from there, you should be able to get yourself an expression now for the kinetic energy. Because when they're at this location, they have both kinetic and potential. Get to it. There it is. So if I wanted the kinetic energy, it would just be mgr minus mgr cos theta. Yeah, that's it. And yeah, that is in terms of theta. No big. Now here's the thing I want you to do next, because I hope this hasn't been lost on you. Kinetic energy is 1/2 mv squared. Centripetal acceleration is v squared over r. There's enough consistency there where when you look at centripetal acceleration, you often have the pieces together to get kinetic energy. So here's what I'd like for you to do. For this person to be traveling in a circular path, there has to be a component of the force towards the center of motion. Can you build a Newton's law relationship to describe the force that acts on them as they slide around this curve. Something that would have in it the centripetal acceleration. Good luck.
Force of the surface, which would be at an angle.
All right, I finally heard it. Draw a free body diagram. That shouldn't have been too hard. Is that where you started? Because there's only two forces acting on them. Name them.
Force and gravity.
The only two forces acting on them, right?
Yeah.
Well, you should probably make your coordinate system aligned with the center, not aligned with gravity, since we want the net force towards the center. So that would suggest the x-axis would be a tangent, and the y-axis would be directed towards the center. Hopefully you're catching up enough with your geometry to realize that has to be theta. We all good there? Any question? So you should be able to break up the weight into its two components. Not a big deal. It's just a ramp. So mg cosine theta here. And there is a component of mg sine theta that's tangent. This is what's causing them to increase their speed. Remember, we've talked about this a little bit, but if conservation of energy suggests that we're using work to convert potential energy into kinetic, then there has to be a force that causes that. The force that's causing that is mg sine theta. That's what's doing the work to change the object's velocity. But at the same moment, there has to be an unbalanced force towards the center to cause the object to be in centripetal motion. That doesn't change. If I make towards the center positive, then that's mg cosine theta minus normal equals m v squared over r. Now, when do they leave the surface? What is the condition? That's right, at the instant that the normal force goes to zero. Now, when you look at this, mg cosine theta minus normal, when you look at that clearly, you should see that the faster you go, the smaller the normal force has to be. Right? Because the right side's getting bigger, the left side has a constant, or I'm sorry, a value that's getting a little bigger, but the normal force has to reduce. So my expectation is that there's going to be a point where the normal force is zero. If I multiply both sides by r, oops, hold on. If I multiply both sides by r, I get just mv squared on the other side. In fact, if I divide this by 2, I get the same expression I have over here for kinetic energy, correct? I mean, this is kinetic energy now. I could eliminate the velocity and figure out theta. This theta would be where they leave the ice. You guys follow what we're about to do? I'm going to take this and substitute it in for 1/2 mv squared. Everybody good? If not, speak now before we go on. It's kind of messy here. Do you guys be okay with the new page? I come back to this picture, 48 degrees. That's going to be like right about there. You slide down, you come off it right there. And from that point forward, you are a projectile. You are no longer in circular motion. You're a projectile. Now, they used to make these back in the turn of the century, like 1910, 1920, especially up north where it's cold. They'd shave these out of the ice. Kids get on them. They'd have a great time until they caught air and, hit the ground. Now, today, they still make them, but they tend to take the ground and put it right about there. So that when you just are coming off the ice, you can start running away from it. So that's what a lot of these look like now. And how many of you have ever ridden any of those slides like at carnivals, those big ones, the big yellow ones with the bumps in them? You'll notice the bumps are just a little less than this amount of a circle. It's to ensure that you don't catch air, but maybe catch a little feeling like you're about to. That's exactly why they're those size. It's exactly why they look that way. So this is a classic physics question. There's a lot of other ways you can go with this question. Like they'll give you the size of R and ask how fast you'll be going, stuff like that. But the interesting question, the one that tends to be the thing we see is, what is the angle? At what angle do you come off the ride? And what's interesting is the angle's the same regardless of the person, the size of the dome, or anything else like that. This also means if you have something like this, something that's half a ball, like a sphere, and you put a piece of ice on it, you'll see it fly off about this angle. So if you have like a smooth ball at home or something like one of the playground ones, you put ice on it, you'll see it come right off, right about that point. Because it work for anything that's spherical. Fortunately, all the ones that I have bumps all over them, so they don't work so well. But you could try it. Yes, Tyler.
So like a road.
You might not notice these things, but I hope that you will start to notice them a little bit more. If you're in AP1, I would have expected you to start paying attention to this. But the Scorpion is the only ride at Busch Gardens to have a perfectly circular loop. No other ride has one. A full 360-degree circular loop is actually not easy to perform in a roller coaster. There's a lot of reasons why, and I won't go into all the structural ones right now, but most of the loops that you'll see in most of the roller coasters, they cheat a little bit. They change the angle of the loop partway through the loop. You see a lot of things that look like this. Cheating is the wrong word to use here, but you don't have to have the same energy to do some of these, where the radius isn't consistent. You'll also see a lot of barrel rolls, where you're not coming back down in the same horizontal location. They don't exist in the same plane. But the Scorpion does a full 360, and it's the only ride in that park where you can get that. And although there are other rides where you do a circular path, like the Phoenix, a lot of people don't do that ride. They don't really like the way the restraint system makes them feel. And some of you, it changes your voice a little bit, if you know what I'm trying to say. So here's what I would like you to tell me. I would like you to tell me the minimum height. The minimum height that the roller coaster cars would have to be dropped so that they don't lose contact with the track here. Now, this problem shares a lot of similarities with what you just did. And I will point out one important thing. If you believe that the height has to be 2R, you don't understand. Because this minimum height will have to be much greater than 2R. If the height was 2R, if I dropped these from the same height that the top of the loop is, well, because there's no kinetic energy here, there'd be no kinetic energy here. If there's no kinetic energy there, I can't be in centripetal motion. I would get there and just fall right off the track, like a cartoon character. Now, actually, you would never make it there. You would start coming up this side, you wouldn't have the velocity to maintain, and you would fall below it. Now, this has happened to real roller coasters before, where they've run into a problem The cars have lost velocity for some unknown reason, broken wheel, debris on the track, and they do what's called a W, where the roller coaster cars come back along the path instead of completing the loop. Scorpion hasn't, but there's been quite a few that have. The Hulk has. In fact, for one summer, the Hulk was doing it about every hour and a half. It was not a great summer. So, I've asked the question, you provide the answer. All right, if you want a hint, it's on the board. You need to start with the conditions that allow the cart to stay in circular motion. Start with the net force. Both of these forces have to be acting on the cars at the top of that loop. The normal force can pull up, technically, if the cars are locked to the track. But that's not what we're looking for. The conditions that we have under this particular problem are ones that suggest we're looking for the point at which the normal force would slowly go to zero. And the only thing providing a centripetal force would be the weight of the cars. The cars can go faster than that, because that would mean then that there would be normal force required to keep them on the track, and that's okay. They can't go slower than that, because then the normal force would have to pull up on the cars. But right now, we can say that mg plus normal would equal mv squared over r. Now again, this is a constant. This side depends on how fast you're going. It should be clear that the slower you go, the smaller the normal force will be. So the minimum speed you can have would be the one in which the normal force goes to zero. Good? Because once you've done that, you should have no difficulty figuring out how high you have to start the cars, since the starting of the cars grants them gravitational potential energy. We know here the cars are going to have both gravitational potential energy and kinetic energy. It's 2r because, of course, we are at a diameter above the ground. Thus, 2r for the height. So I think you guys know what to do next. You do the work. H has to be 5/2 r. Interesting, though. When you go to Busch Gardens and you look at the Scorpion, look very closely, because this is telling me that the cars need to start 2.5 times the height of the first loop. And they're clearly not even close. Should make you wonder why the Scorpion can get away with this. And it's not because the track is pulling upwards on the cars. It's because roller coasters look different than this. And if you know what's actually happening without looking it up tonight at home, I'll be impressed. I'd be very impressed. Because I'm leaving something out. All right. The last example, which we will not finish, which I would like you to consider. This is a lab we will do not next week, but the week after. I want you to imagine I have a weight on a string. And I'm going to drop it so that it swings downwards to here. The string's length is L. I'm going to put a pin right here so that when the string makes it straight downwards, the string will hit this pin and will bend around it. Where do I place the pin so that the mass is always in uniform circular motion? Meaning, what is the smallest distance where I can place that pin and still have this system in uniform circular motion? This problem's a little tricky, but there's nothing here that's different than the last two questions. All I've really done is replace tension for normal force. If you think of it that way, you should be able to come to school tomorrow with D in terms of L. And I'll even put the fraction online tonight so you can check your work. But try it. I'll give you a hint. The system starts with that much energy. I know, ridiculous thing to tell you, but you can do the rest. I believe in all of you. So I have mgr minus mgr cos theta, and that equals kinetic energy, which we just showed then equals 1/2 mgr cos theta. Everybody good? Well, I'm hoping you notice I can cancel out the mgr, the mgr, and the mgr. Which means it doesn't matter who's there, how big the dome is, or what planet it's on. It'll be the same for everybody. Every place, everywhere. So 1 minus cosine theta equals 1/2. One half cosine theta. That's what I said. So cosine theta equals 2/3. You can do the math, but when you add 1 to 1/2, you get 3/2. Multiply both sides by 2/3, you get 2/3. All right, well, what is it? That's an angle. That's not arbitrary. It's not based on R, theta, G. This is an angle. This is an answer. What is it? 48.2 degrees. That's the magic number right there.